Welcome to Reasonable Data Science, the channel devoted to teaching a reasonable amount of data science in a reasonable amount of time. This video is going to be really exciting because it's going to demonstrate how to build a logistic regression model to predict if a passenger survived or died on the Titanic. After we build the logistic regression model, we'll then learn how to test whether the model accurately predicts or classifies whether a passenger survived or died on the Titanic. So in order to build a logistic regression model, we need to load a few libraries. If you've been following my other videos, you'll be familiar with some of the libraries shown on the screen here. But some of the new ones we'll need to import statsmodel.api. This will give us that's the library for the logistic regression model. We've already learned that the train test split from video 5 here, that's to create training and test data sets. And then down here in the import metrics package, we're going to import two new ones. We're going to import the confusion matrix display, and we're also going to import the recall score. I've already gone ahead and run also the two functions here that will display 1,000 rows in any table and will display all of the columns. And then lastly, I've already set up the data set here. So we're going to be using the Titanic data set that we've been using throughout this video series. And so let's just take a quick look at what this looks like. We're going to say df.head, and we'll just look at the first few rows. And so this is not the actual data set that we downloaded from Kaggle.com. In video 4 of this series, we actually went and cleaned up the data. So we replaced all the missing values with the median, and then we eliminated some of the columns. So we were left with this really smaller data set, but for this video, using the smaller data set will be a lot easier for us to manage when building our first logistic regression model. Before beginning any logistic regression model, what I like to do is I like to see the frequency of the target variable that we're trying to classify. And so in this data set, the variable we're going to try and classify is the survived variable. And so I just like to see the distribution to see how many ones and how many zeros are in this data set. So if we say df of survived dot value underscore counts, and then we say normalize equals true, drop NA equals false, this will give us the distribution of the values in the data set. And so we can see here that 61% of the values in the data set, or in our target column here, are zeros, which means that 61% of the passengers in this data set died. 38% of the passengers in this data set are a 1, or that means they survived on the Titanic. So what that means is that this data set is very heavily skewed toward passengers dying, which when we remember what happened in the Titanic, that makes sense. Most of the passengers on the ship died, unfortunately. So when we get down to the testing stage of a logistic regression model, it might not be a surprise if our logistic regression model is better at predicting people who died versus people who survived, just because 60-some% of the data set is passengers who died. But before we make the logistic regression model, we do need to do a little bit of feature engineering here. So just like we learned in video 5 with linear regression, logistic regression also needs to create dummy variables when you want to include any sort of non-numeric or categorical data. And so we'll have to create dummy variables for the p-class variable here, because even though it shows it's numeric, the class of a passenger is actually a category. And so we'll want to break p-class into those dummy variables so we can accurately include it. Otherwise, if we don't break it into dummy variables, the logistic regression model will treat it as a continuous variable, and you could end up predicting a class of, let's say, 2.5 or 1.75, which that doesn't exist. You either are first class, second class, or third class, so you're unique category. Also, we need to change and create dummy variables for the gender column here of male. And so let's create those two dummy variables. We're just going to say df equals pd.get_dummies. Then we're going to say df, and then we're going to say columns equal p-class and gender. And then I'm going to say drop underscore first equals false, and then dtype equals int. And then if we look at df.head, we should be able to see all those new columns that we created here. And so as you can see, there's 3 new columns for first, second, and third class, and then 2 columns for whether it was a female passenger or a male passenger. So the next step after getting your data set up with dummy variables is we're going to create our y and our x data sets, which we'll then use those to create our training and our test data sets. So our y variable is our dependent variable or our target variable, the one we're trying to predict. So we're going to say y equals df of survived. And then we're going to say x equals df dot iloc. And then what we're going to do is we're going to do a colon, comma, 1, colon. And what that'll do is that'll grab all of the variables to the right of the first column here, which is survive. So we want to include all of these variables in our X data set here. And so if you run that, you won't see anything. But what we can then do is we can set up our 4 training and test data sets. We're going to say X underscore train, X underscore test, Y underscore train, Y underscore test. And then we're going to set that equal to our train underscore test underscore split. And then within this function, we need to say x comma y. So we're going to split our x and our y variables into the 4 training and test data sets. And then I want to have a test data set size of 20%. So we're going to say test underscore size equals 0.2. And then random underscore state equals 0. So it's always important to include this random underscore state because this train test split will grab a random 20% of the rows and stuff them into our test data sets. And so if you ever want to go and try and recreate this within this session, you'll want to type in random state equals 0, and that'll get you the exact same random split. Otherwise, you'll never get the same split because it's random. So if we run that, you won't see anything, but what we can then do is we can look at what our data sets look like. So if you look at y underscore train dot head, and we run that, that is just the survived column. So it's 80% of the rows of the survived column are in the y train. If we look at the x train data set and say dot head, it should be all the other variables excluding the survive. So we have all of our other x variables here that we're going to use to predict whether a passenger survived or died. All right, so the next thing we're going to do now, since we have our training and our test data sets set up, is we're going to actually create a 1 variable logistic regression model. And so I like to set it equal to an output or an output variable. So I'm just going to call this logistic model, and I'm going to set that equal to sm.logit. And that's the function for the logistic regression is sm.logit. And then we're going to say y underscore train. That's the variable we're trying to classify or predict. And then we're going to say sm.add underscore constant. And then we're going to say x underscore train. And then right now we're just going to use the age variable to try and predict whether a passenger survived or died. So then we're going to say fit at the end of that. And then I'm going to say print logistic model dot summary, open close parenthesis, and then one final parenthesis. We run that, we'll get the logistic regression output table here. And so a few things to point out. The first thing you'll notice is the dependent variable in the table shows survived, which that's correct because we're trying to predict whether someone survived or not. You'll notice down here is the coefficients. And this is the most important part of the logistic regression model because this shows the relationship between age, and our dependent variable survived. But one odd thing about logistic regression is that the coefficients are in the terms of log odds. So log odds are kind of weird. And so how you would interpret this variable is that for every 1 unit change in the age, the log odds of survival decreases by minus 0.0133. So don't worry if you're confused, because I'm confused as well. Log odds are tricky. But what we can do eventually is we can actually change this from log odds to probability, and that'll make a lot more sense to us. But before we do that, if we wanted to actually use the output of the logistic regression model, we can just use this equation that we've set up here. And so if we wanted to look at logistic model dot params, and then we can say dot iloc of 1, actually let's do a 0. This will give us our constant value from the table here. And so if we use this dot params dot iloc functions, we can then just build the equation to try and predict whether a passenger survived or not on the Titanic. And so I'm just going to set this up to a variable called prediction. I'm going to set that equal to logistic model.params, our constant. And then I'm going to say plus logistic model.params.iloc of 1. And then let's say we wanted to predict someone with the age of 32, so a 32-year-old passenger. Let's predict a 32-year-old passenger and what their log odds of survival would be. So we'd say 32, and then we'll run that here. We won't see anything, but if we said print prediction and ran that, sorry, print prediction, not predictions, we'll get a log odds of minus 0.53. So a 32-year-old passenger had minus 0.53 log odds of surviving the Titanic. But again, log odds is not really super helpful. So what we need to do is we need to transform this from log odds to probability. And the probability will be much more useful to us in determining whether this passenger who is 32 years old actually survived the Titanic. So to do that, we need to use the exponential function. So we're just going to say np.exp, say prediction, take that divided by 1 plus np.exp, and do prediction. And so when we run that, we'll get now a probability for this passenger. So a 32-year-old passenger had a 0.36 probability of surviving the Titanic. So one of the general rules of thumb with logistic regression is that when a probability is less than or equal to 0.5 or 50%, then the model is going to classify that data point as a 0. So in this case, since 0.36 is less than 0.5, our logistic regression model would classify a 32-year-old passenger as having died on the Titanic. But again, we're only using one variable, age. So our model's probably not explaining the relationship between the true relationship of survived very well. So let's go and add a second variable here to the model. So I'm just going to come up and copy what we did before and paste this down below. After we've pasted this in, we're going to add our fare variable to our logistic regression function here. The first thing though is make sure to add a double bracket around it since we're adding another variable. So we're going to say age, comma, fare. And like I said, just remember to add 2 brackets around it, otherwise you'll get an error. So let's run that, and then we'll see our logistic regression output. And so again, survived is our dependent variable, stayed the same. In the coefficients down here, now added to our age, we've added fare. And so age still is interpreted the same, it looks like. for every 1 unit change in age, it's a negative log odds of survival. But fair has the opposite relationship. So every 1 unit change in the fair, it looks like it has a positive change to our log odds of survival. And so that to me says the more you paid for your ticket, the higher chances you had of surviving the Titanic versus age, the older you were for age, the less likely you were to survive on the Titanic. But let's come up here and we'll use our prediction equation that we did before. So let's predict a 32-year-old passenger who paid $50 for their fare on the Titanic. So to do that, we're going to leave the first two statements in our equation the same because the first one is for age. Now we're just going to add a second one. So we're just going to say plus logistic model.params.iloc of 2. And then we're going to take that times 50 because our passenger paid $50 for their fare. And so then we'll say print prediction after we've run this here. So we get for someone who is 32 years old who paid $50 for their fare, their log odds of survival is minus 0.258. Again, log odds, not very helpful. So let's change that from log odds to probability. We're just going to say np.exp prediction divided by 1 plus np.exp of prediction. We run that, we get 0.43. So it looks like a passenger who is 32 years old, paid $50 for their ticket, has a 43% probability of surviving the Titanic. Again, the general rule of thumb with logistic regression is that the threshold to classify whether something's a 0 or 1 is 50%. So since 43% is less than or equal to 50%, our model is still going to say that this passenger died on the Titanic. It's going to classify them as a 0. So that's using two continuous variables in the logistic regression model. Let's now add in some non-continuous variables or some categorical variables. But first, let's look at our xtrain data set again. We're going to say xtrain.head. And so we've added in age, we've added in fare. Now let's add in the p-class and the gender variables. So just like with linear regression, logistic regression for dummy variables, you have to always exclude one of the unique values. So since we have three p classes, we're going to only include 2 of them in our model. Since there's 2 gender variables, we're only going to include 1 of them. So rule of thumb is you always take the number of dummy variables minus 1, and that's the amount to include in your model. And so in our model, let's include second and third class, and then let's include the gender males in our model here. So I'm just going to come back up and copy what we've done before, just so it's a little bit easier. And then after the fare, I'm just going to add in p-class underscore 2, p-class underscore 3, and then gender underscore male. And then let's run that. And we should get the logistic regression output, which we do. Again, our dependent variable is still the survived, but now we've added a bunch more coefficients. So it looks like the age coefficient is still showing a very negative relationship. But wait, when we added in fare now, it looks like that flipped to a negative relationship as well, which was interesting because before it was positive. How do we interpret our dummy variables or our categorical variables? Well, since we included p-class 2 and 3 in our model here, the output or the coefficients are in reference to p-class of 1. So it looks like if you're a second class passenger, your log odds of survival are negative 1.08 compared to a first class passenger. If you're a third class passenger, your log odds of survival are minus 2.3, lower than a first class passenger. So in theory, that's making sense because what I remember from watching the movie Titanic is that first class passengers were able to get on the lifeboats before second and third class. So therefore, if you were in second and third class, your chances of surviving are much lower than if you were first class. Now, how about gender male? Well, it looks like males have a minus 2.67 lower log odds of surviving compared to females, which again, when I remember watching the Titanic movie back 20 years ago, it showed that males were the last to get on the lifeboats. It was women and children first. So this makes a lot of sense that males have a lower chance of survival compared to females. But let's actually test this out and classify a passenger like we've been doing. So I'm going to come back up here, just grab our prediction equation and paste it down here. So let's add in and try and classify a passenger who is 32 years old, paid $50 for their fare or their ticket, and let's say they were third class. So let's add in another term to our equation. So I'm just going to copy this, paste it in here, change this to 3. So this is our second class variable. So we're going to take it times 0 because second class is our third variable. Copy this again, paste it down here. Now we're going to say 4. And this one we're actually going to take times 1 because our passenger is in third class. So third class is the third coefficient in our output. So we're taking this, it's our fourth one, sorry, and we're taking this times 1. And then let's say that our passenger is a male. So then we're going to take the fifth coefficient here times a 1 as well because they're a male. Change this to a 5, and then take this times 1. And just make sure to finish off the parenthesis there. So let's run that. And I have an extra parenthesis in there, an extra plus on accident. So let's rerun this again. And we get a log odds of minus 2.59 for this passenger. So someone who's 32 years old, paid $50 for their ticket, was in third class, and was a male, had a minus 2.59 log odds of survival. But to really see how our model would classify this passenger, we're going to take the log odds of 2.59 and transform that into probabilities. So we're going to say np.exp of prediction divided by 1 plus np.exp of prediction. And when we get that, this passenger here who's 32 years old, paid $50 for their ticket, was in third class and was a male, has a probability of survival of 6%, it looks like. So since 6% is lower than our 50% threshold, our model is going to classify this passenger as having died on the Titanic or make them a 0. What's really fun about when you set up your logistic equation like this is that you can test a couple different things real quick. So if we wanted to say, well, what if the passenger was the same passenger, but they were female? So we just change our gender male coefficient to a 0, rerun it, and then we'll rerun to get the probability. And it looks like, ooh, they changed quite significantly. So a male only had a 6 or 7% probability of surviving the Titanic, but a female who is the same female had a 51 or 52% probability of survival. So our model would actually say this passenger right here survived because their probability is just over 50%, or a 50% threshold. So that's the fun thing about once you build this up, is that you can just test it and see all the different combinations of variables. Let's say our passenger was in first class, so we're going to make the second class coefficient times 0 and the third class coefficient times 0. So they were a 32-year-old who paid $50 and were in first class. $50 might be too low for a first class ticket, but let's just check it out anyways. They had a 91% probability of surviving. So a female who was in first class, 32 years old, paid $50, had a 91% probability of survival. So kind of a fun way to test it out here. But really the best way to test how well the logistic regression model is classifying the data is by using the test data sets. So let's look at what our test data sets are again. So let's just say y_test.head. And the y underscore test is survived. So basically the y underscore test is 20% of our original data set and then just using the survived column. So that means when we use x underscore test dot head, that'll be 80% or 20% of the rows of our original data set, just all of the variables excluding survived. So what we're going to do now is we're going to take our logistic regression model, which is this one here, which consists of age, fair, the P classes, and the genders. And we're going to apply this logistic regression model to our test data sets. And then that'll allow us to see how well it predicts the data it hasn't seen before. And so what we're going to do is we're going to apply the model and then put it into a new column in our y-test data set. So we're going to create a new column in y-test and call it predicted. So we're going to say predicted. And then we're going to set that equal to logistic model, which is, if we scroll back up here, this is the name of our logistic model that we created. So logistic model. So we're just using that down here again. So we're going to say logistic model, and then we're going to say dot predict. And then within this function, we're going to say sm.add underscore constant. And then we're going to say x underscore test. And this is where you need to add in all of our variables that we included in our model up here. So I'm just going to go and copy what we did before. That way it gets in the same exact order and nothing's off. It's really important that you get it in the same exact order, otherwise your predictions could be off when you do this. So I'm just going to close off the double brackets, close off the double parentheses. And then let's look at y underscore test.head once we run this. And so as you can see, we have our original survived column in our y-test. We've now added a prediction or a predicted column to it, which predicts whether a passenger has survived or died. So what's nice about using this predict function is that it automatically outputs it into probabilities. You don't need to transform this from log odds to probabilities when you use the predict function here. And so this is saying that for passenger 495, their survived classification is they died. And then our model gives them a probability of survival of 0.21. Since 0.21 is less than 50%, our model should say that this passenger died as well. But what we can do is we can overwrite our predicted with that same general rule of thumb. So we're just going to say y underscore test and then predicted. And then we're going to say np.where y underscore test of predicted. And if it's greater than 0.50, we're going to transform it to a 1. So anytime this probability here is greater than 0.5, we're going to change it from a probability to a 1. Anytime it's less than or equal to 0.5, we're going to give it a 0. And so then if we were to run y-test again after we run that function, it's changed it from probabilities now to 0 and 1 classifications here. So what we could do is we could just go row by row and see like, oh, it looks like our model accurately predicted this one. Oh, look, this passenger survived, but our model predicted they died. So we were off on that one. We could go row by row and do that, but that's really tedious. So instead, what we're going to use is a confusion matrix. And so a confusion matrix just gives you a 2x2 grid that lists how accurate your model predicted or classified the data. So to build a confusion matrix, we're just going to say set it equal to a variable called conf matrix. And then we're going to set this equal to confusion matrix display dot from underscore predictions. And then we're going to say y underscore test of survived. And I'm just going to come down here and do that way it's easier for you to see on the screen. Then we're going to say y underscore test of predicted. Say labels equal 0, 1. Very important that you add this in because this tells you the order of your confusion matrix. We're going to start with 0 values first, and then 1 values, or basically negative and true values here. And then I'm going to say color bar equals false. We don't need to show a color bar for this. And then I'm going to say display underscore labels equals died, which is a 0. And then survived. And this part here is completely unnecessary, but I just think it makes it easier for us to read it. So that's why I'm doing it. I'm going to say survived of 1. And you notice that my 0 and 1 labels follow the same 0 and 1 labels that I put here. Very important that you do that. And I'm going to close off the bracket here and close off this parenthesis. All right, after we close off that parenthesis, I'm then just going to make the confusion matrix just a little bit fancier. So I'm going to write some functions here, some code to just change the labels up. Completely unnecessary, but I just like seeing it this way. So I'm going to say plt.x label predicted, plt.y label of actual, and then I'm going to say ax equals conf matrix dot ax underscore. And what this will allow us to do is set all of our axis labels to the top. So we're going to say ax.x axis dot tick underscore top, ax.x axis dot set underscore label underscore position, and we're going to say put that one at the top as well. Now finally we can just say plt.show. And what this shows is the confusion matrix of how well our logistic regression model accurately classified the test data set. So the two squares or tiles that you're going to want to really check out first are the 0, 0, one here in the top left corner. So what this says is that our logistic regression model predicted that this passenger died, and then the passenger in the test data set actually died. So it accurately predicted 90 passengers that died. So that's that top left corner here. The bottom right corner is the number of passengers it actually predicted that survived. So our logistic regression model predicted that a passenger survived. And then when we go over here, it actually survived. So 47 times it predicted that the passenger survived when they actually died. Unfortunately, our model has some errors in it. So if we look at the top right corner here, our model predicted that the passenger survived, but in actuality they died. So our model did that 17 times on the test data set. So we got 17 of the passengers incorrectly classified. And then over here, our model predicted that the passenger died when in actuality, the passenger survived. So it did this 25 times. It classified a passenger as having died when they actually survived. So our model does have some error in it. But if we wanted to see how accurate our model really was, we can use the accuracy score function. So we're just going to say accuracy underscore score, and then we're going to say y test of survived, and then y underscore test of predicted. And when we run this, this will give us our accuracy score. Sorry, throw in the metrics.accuracy score before that. So this shows that our model was 76% accurate overall, which, I mean, when we look at it, we didn't really do a ton of prep work on our data set. So coming up with a 76, 77% accuracy score is pretty good. If you don't want to use the accuracy score function, what you could just do is you could just use the confusion matrix. So essentially what it's saying is that how many did we get right? So we got 90 predictions right, plus 47 predictions right, divided by the total amount of predictions in the data set. So 90 plus 17 plus 25 plus 47. And that should also give us our same accuracy score, 76%. How much did our model get wrong? Well, essentially it got 1 minus the accuracy score wrong, or it misclassified 1 minus if we take the accuracy score. So our model misclassified 23% of the data. So basically if we were to take 17 plus 25 and then divided by all of the rows in the data, we'll get the same misclassification. So that's how to calculate accuracy in the error of our model. But if you remember at the beginning of the video, we learned that 60% of the data set was passengers that died. So we theorized that possibly our logistic regression model was better at predicting passengers who died versus passengers who survived. Well, there's two metrics we can use to test that. One is called the sensitivity, and that's looking at how many times or what percentage of the time our model accurately predicted a passenger that survived when they were survived. So we can use the function recall underscore score, and then we do y underscore test of survived, and then y underscore test of predicted. And then we're going to say POS underscore label equals 1. And it looks like our model accurately predicted the true or the passengers surviving 65% of the time. So really what that's saying is that when our model accurately predicted 47 passengers who survived. So we predicted a 1 here, and it was actually 1. But it only predicted 47 out of 47 plus 25. So if we were to say 47 divided by 47 plus 25 from the confusion matrix, we should get the same 65% as that recall score function showed here, which again, our model accurately predicts 65% of the time a passenger who survived. We can do the inverse. We can look at the specificity, it's called, which is how many times did our logistic regression model predict a passenger who died accurately. So basically, our model predicted 90 times a passenger who died accurately, but that 90 is 90 divided by 90 plus 17. And so if we were to take 90 divided by 90 plus 17, this will give us the specificity of the model, 84%. So our model accurately predicted passengers who died 84% of the time. But we could also use this recall function here. So I'm just going to come up here and copy it. And instead of saying position labels equal 1, we're going to say position labels equal 0. And that should give us the same 84% for specificity here. So again, 84% of the time, our model accurately predicts a passenger who died. So as we theorized in the beginning, our model is a lot better at predicting passengers who died compared to passengers who lived. And that's solely because 2/3 of the data that we trained our model on is passengers who died. So it's being skewed toward the passengers being died is how it's classifying them. That was a quick tutorial on how to set up and build a logistic regression model. I hope this video was helpful. If it was, please like and subscribe to my channel for great future content coming up. If you haven't checked out the other series or videos in this series, go to my page, Reasonable Data Science, and follow along. Thank you.